Statistics 3, confidence interval for a mean. Type 3, find again which is our sample size. So in the first example here, I'm going to call this 1 and 2. So in example 1, what we have is a random sample of 250 cars were taken and the mean age of the cars was 4.5. The standard deviation was 2.2 years. And the first one is to find the 95% confidence interval for the mean age of all the cars. So our 95% confidence interval for the mean is our sample mean plus or minus our margin of error. So our critical value for our 95% confidence interval is 1.96 times our standard error of the mean, which is sigma over root n. So what have we got? Well, our sample mean is 4.5 years. Our standard deviation is 2.2 years. And our sample size here is 250 cars. So if I expand that formula, we have our sample mean minus 1.96 times sigma over root n less than or equal to mu, our population mean, which is less than or equal to our sample mean plus our margin of error, so 1.96 times the standard error of the mean. So subbing all of our values in, what we have is 4.5 minus 1.96 times 2.2 over the square root of 250, less than or equal to our population mean, which is less than or equal to 4.5 plus 1.96 times 2.2 over root n. So if I put all of that into my calculator, well, what do we get? So we should get 4.227 less than or equal to mu, our population mean, which is less than or equal to 4.773. So in other words, what we can say is with 95% confidence that our true population mean, and this time, we really need to start putting these into context. So in other words, we can say with 95% confidence that the mean age of all cars in the population lies within the interval of 4.227 years and 4.773 years. So it's always really important to add in our sentence to kind of put it into context. And rather than just saying, we can say with a 95% confidence that the true population mean lies within the interval. Well, what is the true population mean that we're referring to? So we really want to kind of get into the nitty gritty of it from here on in, okay? So part 2 then says, well, what sample size is required to estimate the mean age within plus or minus 0.3 years. So we're looking for the sample size. We're clearly told it's a 95% confidence interval, which means that our critical value that we can use for this question is our 1.96. Okay, so let's look at part 2 of the question. Let me just go back. Just label this part 1. So what are we given? We're given the plus or minus, within plus or minus 3 years. So that's basically our margin of error. So the margin of error is E. And what is E? Well, E is our plus or minus 1.96 sigma over root n. So our margin of error, we're told, must lie within plus or minus 0.3 years. Now we know our sigma is 2.2 years, our standard deviation. We know it's 95% confidence interval. So therefore our critical value is 1.96, okay? So we can't use our critical values unless we know it's a 95% confidence interval. And therefore we're looking for what is n. So of course the plus or minuses are going to cancel here. So I'm just literally saying 0.3 is equal to our 1.96 times sigma, which is 2.2. And that's all over the square root of n. So if I rearrange that, I get the square root of n is equal to 1.96 times 2.2 divided by 0.3. And of course, I really don't like especially in these questions, better off simplifying at the end rather than all the way through the question. Otherwise, you're going to get a little bit further and further away from the true answer. So if I square both sides, well, what do we get? So what we get is 206.5927111. Okay, now n has to be a natural number, and we know that it has to lie within the limits of 0.3. So n therefore is 207 cars. Now if you're not sure, you can always check this, right? So I mean, if I was to say 1.96 times 2.2 over the square root of 207, well, what that gives me is 0.2997, right? So if I sub 207 into the formula, that gives me E is equal to 0.299, right? So in other words, that's less than my 0.3. Whereas if I actually was to round down and I was to put in 206 in, and I put if I put 206 in, so if I was rounding this n value down, well, what would that give me? Well, that gives me 1.96 times 2.2 over the square root of 206. And what that gives me is 0.30043125. So you can see, even if you're not sure whether you have to round up or round down, if you sub it back in quickly, you can clearly see that it's lying outside. So that's greater than the margin of error range, because we wanted it within the 0.3 years. So therefore it has to be just under. So really important that, just to make sure that you're giving the correct answer there. Okay, so the next one then is, well, what happens if we're looking at changing the sample size, okay? So we're going to look at example 2 here, where we have a random sample of, again, our sample size is 144 males, and these are students that are studying in a large university, and their heights are measured. Our mean height of the sample is 175 centimetres, and the standard deviation of all the males in the university was 9 centimetres. So you can see we're not given, as I said to you in the PowerPoint, it's rare we're ever given the sample standard deviation. So we always take the population standard deviation if that's the case, okay? So the first thing, again, we want to do is get our 95% confidence interval of the heights. And again, the 95% confidence interval implies our critical value is going to be 1.96. Okay, so we want our 95% confidence interval for the mean. So we have our sample mean plus or minus 1.96 sigma over root n. And again, remembering that our standard error of the mean is page 34 in your maths tables. Whereas this formula for your 95% confidence interval is not in it. So the only thing that's in your maths tables is the sigma over the root n. Okay, so let's put that in. Well, what's our sample mean? Well, our sample mean is 175 centimetres. Our standard deviation is 9 centimetres. And our sample size is 144. So if I expand that formula, And then I sub in my values. Well, we have 175 minus 1.96 times 9 over the square root of 144, less than or equal to mu, less than or equal to 175 plus 1.96 times 9 over the square root of 144. So subbing in our values there into our calculator, well, what does that give us? Well, we get 173.53 less than or equal to our true population mean, less than or equal to 176.47. So that's the 95% confidence interval. In other words, what we can say is we can say with 95% confidence that the true population mean, and what is our true population mean? Let's go back. So that our true, that the mean height of students, male students, so we can say with 95% confidence that the true mean height of male students in the university lies within the interval of 173.53 centimeters and 176.47 centimeters. It's squished there at the end. Okay, so what happens next then in part 2? It says, show that the confidence interval would decrease if the sample size was 225. So in other words, if we increase the sample size, that the confidence interval is now going to decrease. So obviously the more samples we take, we saw in the video that has an knock-on effect on the confidence interval. And obviously it kind of narrows your interval range, so you're getting closer to the true value there. Okay, so part 2. So again, we're looking at a 95% confidence interval for the mean. So sample mean plus or minus our margin of error. This time n is 225. Sample mean is 175 centimeters. Standard deviation is still 9 centimeters. Okay, so expanding our equation. And subbing in our values. So we have 175 minus 1.96 times sigma, which is 9 over the square root, this time of 225, is less than or equal to the true population mean, which is less than or equal to 175 plus 1.96 times sigma, which is 9 over the square root of 225. Okay, so subbing those values in, then we end up with 173.824, less than or equal to the true population mean, less than or equal to 176.176. So now we have our 95% confidence interval. So what we can say is, i.e., we can see that as the sample size increases, the confidence interval decreases. As the standard error of the mean is going to decrease. Because you've got a bigger sample, so your error is going to be much smaller. Okay, so again, you can see we have 173 to 176, whereas we go back from 173.53 to 176.47. So just marginally smaller. Okay.